And
Now it's on.
okay.
Okay, let's welcome Pia Smedsrud.
Okay.
Also from Oslo, and also giving us a more medical perspective on the whole thing.
Yes. So, just a short presentation. I did this together with Stephen Hicks. We're from Simla. I'm also a physician, and I've been trying to get into your field for the past 3 months. So, pardon if my lingo is a bit off, then you know why. So, our hypothesis for this approach was trying to do transfer learning from 2 different domains. So one was networks pre-trained on ImageNet and the weights from there, and the other one was to combine a new medical dataset that we train the networks on and see if that made any difference. So this is our typical ImageNet image on your left side, which are notably different from the Medico dataset. And this was our new dataset. We combined pictures from one cataract surgery dataset. Cataract is an eye disease that you perform surgery on, and the other one was laparoscopic pictures from laparoscopic surgery. That means camera surgery from inside the bowel. In addition to this, we we weighted the network loss because the classes had very different sizes. One class had only 4 pictures and another class could have more than 600 pictures. We did some various data augmentation, flipping, rotating, zooming, stuff like that. We did L1 and L2 regularization. And then for the outpatient class, which we also had problems with, we treated it as an unknown class, just putting the rest of the pictures that didn't get in any other classes. And we also extended it just by taking some random photos from office settings, because it had only 4 images to begin with. We did our training, and training was done both in PyTorch and also in the Keras TensorFlow. And we did a 3-fold cross-validation. The evaluation, we have a confusion matrix, which I will show you. And was one question earlier. And the organizers did a macro averaging, which is why the metrics are as they are. So our results, as you can see, our best method was the 3 average DenseNet 169, which had quite good MCC. And we also submitted to the efficiency task, subtask. So we just put the same networks to work, but this time with a focus on the FPS, the frames per second, so the speed. Turns out that we had a lot of the same problems as everyone else. We were back with the esophagitis and the normal Z-line confusion, and we have also the dyed lifted polyps versus the dyed resection margins, which I will come back to, and also some confusion in the instruments class, which might be because in those images there are other classes represented, such as, for example, polyps. So this is examples from the esophagitis and the normal Z-line. So all our networks seem to have no problem classifying the example images with the severe examples of esophagitis, where there were ulcers and bleedings and stuff like that. But all the images where you can really see no big difference, which is, as Thomas said, it was the same images that experts would have problems between in distinguishing between. Which is, as you said, Matthias, might be a positive thing, actually. And we also had this dyed lifted polyp and dyed resection margin problem. So our conclusion was, in fact, that the the networks trained with the ImageNet on the ImageNet images were performing better than the transfer learning from the medical images. And for the efficiency task, we found that the networks with lesser depth were more efficient and got a higher number of FPS. I think we could do more work on this. I think that there might be some potential in trying this more domain-specific transfer learning. But for now, we couldn't find it to be better. But we also had some limited amount of time, and training the network from scratch took a lot of time, which meant we couldn't try out a lot of different networks or architectures because it took a lot of time. It took up to 3 days just training one network from scratch. So that sort of limited it for us. Okay? Thank you.